What if I told you that everything you see around you, the screen you're watching, the air you're breathing, the very planet beneath your feet, all began as a single, incomprehensible point smaller than an atom? What existed before time itself began ticking? What cosmic forces sculpted the very fabric of reality in those first unimaginable moments? These aren't just philosophical questions. They're the deepest mysteries at the heart of modern cosmology, mysteries that scientists have been wrestling with for generations. And despite all our advances, the true story of our universe's birth remains one of the most compelling and elusive puzzles of all time. Imagine rewinding the cosmic clock some 13.8 billion years to a moment so extreme that our laws of physics break down. A moment of infinite density, infinite temperature, a singularity that gave rise to everything. We call it the Big Bang, but that name hardly captures the sheer explosive creativity of those first instants. In less time than it takes to blink, the universe expanded from something smaller than a proton to something larger than a galaxy. And within those fleeting moments, the seeds were sown for stars, planets, and life itself. But what really happened in those first fractions of a second? How did something come from nothing, and why does the universe look the way it does today? That's exactly what we're going to explore together in this video. We're about to journey through 30 of the most fascinating, mind-bending theories scientists have proposed to explain the universe's first moments. From cosmic inflation to brains colliding in higher dimensions, from quantum fluctuations to holographic principles, each theory offers a unique glimpse into how it all might have begun. Some are widely accepted, others live on the wild frontiers of physics, but each one reflects humanity's relentless curiosity, our drive to understand not just where we came from, but why we're here at all. So settle in, open your mind, and get ready to explore the greatest story ever told, the story of how everything began. Our journey begins with the most famous and well-supported explanation for our cosmic origins, the Big Bang Theory. It proposes that the universe wasn't always here, that it actually had a definite beginning, a moment of creation from which space and time themselves emerged. Picture this not as an explosion in space, but as the sudden, rapid expansion of space itself, everywhere at once. From an initial state of unimaginable density and heat, a singularity where the known laws of physics simply ceased to function, the entire cosmos began to expand and cool, eventually forming the galaxies, stars, and planets we see today. But how can we be so confident about an event that occurred nearly 14 billion years ago? The evidence is written across the sky. In the 1920s, astronomer Edwin Hubble made a revolutionary observation. By analyzing the light from distant galaxies, he noticed their light was shifted toward the red end of the electromagnetic spectrum. This redshift wasn't a random finding. It showed that galaxies are moving away from us, and crucially, the farther away a galaxy is, the faster it appears to be receding. This isn't because we're at the center of some grand exodus, but because the very fabric of space between all galaxies is stretching, carrying them apart like raisins in a rising loaf of raisin bread. This observation, now known as Hubble's law, provides a powerful and direct line of evidence that the universe is indeed expanding, implying it was once much smaller and denser. The next great pillar of evidence came from a seemingly mundane source, static. In the 1960s, Arno Penzias and Robert Wilson were using a large radio antenna and were plagued by a persistent, faint hum that came from every direction in the sky, day and night. They initially thought it was caused by pigeons nesting in the antenna, but even after cleaning it, the signal remained. What they had accidentally discovered was the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. This is the remnant heat from the universe's early, ultra-hot phase, now cooled by expansion to just a few degrees above absolute zero. This discovery was the smoking gun, the definitive proof that our universe did indeed evolve from a hot, dense state. It's the oldest light we can see, a snapshot of the infant universe when it was just 380,000 years old. Visualizing this expansion is key to understanding. Imagine running the cosmic film in reverse, watching all the galaxies draw closer together until everything that exists is compressed into an infinitesimally small hot point. The Big Bang is that moment we hit play again. In the first fraction of a second, the universe expanded faster than the speed of light during a period known as inflation, smoothing it out and setting the stage for the formation of all future structure. From that primeval inferno, the first particles coalesced, then the first simple atoms, and eventually, over billions of years, the magnificent cosmic structures we observe today. While the Big Bang theory doesn't attempt to explain the initial singularity itself, what caused it or what came before, it provides our most complete and tested narrative for the evolution of our universe from its earliest moments to the present day. But as robust as the Big Bang theory is, it left cosmologists with some deeply puzzling questions about the initial conditions of our universe. Why is the cosmos so remarkably uniform in every direction we look? And why is the geometry of space so perfectly flat, balanced precisely on the knife's edge between eternal expansion and eventual collapse? These weren't just minor curiosities, they were fundamental problems that pointed to gaps in our understanding. The horizon problem asks how regions of the universe on opposite sides of the sky could have such identical temperatures when, according to standard Big Bang calculations, they never had time to exchange heat or information. They were never in causal contact. It's like walking into a vast concert hall and finding thousands of people you've never met all humming the same exact note in perfect unison. How could such perfect coordination have occurred? Then, in the late 1970s, a young physicist named Alan Guth had a moment of profound insight that would reshape our entire cosmic origin story. While working on a related problem in particle physics, he realized that a peculiar state of matter, a false vacuum, could generate a repulsive gravitational force. This negative pressure wouldn't just push things apart, it would cause the very fabric of space itself to expand at an exponential, staggering rate. Guth had stumbled upon the mechanism for cosmic inflation, a theory proposing that in the first incomprehensibly tiny fraction of a second, the universe underwent a violent growth spurt, expanding faster than the speed of light by a factor of at least 10 to the 26. To put that in perspective, in less time than it takes a beam of light to cross a single atomic nucleus, a region smaller than a proton was stretched to a size larger than our entire observable universe today. This monumental expansion elegantly solves the horizon problem. Before inflation, the entire observable universe was a tiny, subatomic patch that was thoroughly mixed and thermally equilibrated. It was all in contact with itself. Inflation then took this tiny, uniform region and stretched it to cosmic proportions, preserving that pristine uniformity across vast distances that only later would become causally disconnected. The flatness problem also finds its resolution. Imagine taking a small, crumpled piece of paper. Its surface is full of wrinkles and curves. Now blow it up to the size of a football field. The tiny Chinese letter IZED wrinkles smooth out and the curvature becomes imperceptible. The surface appears flat. Inflation did exactly this to the fabric of space-time, stretching any initial curvature so dramatically that the universe we observe today appears geometrically flat. The most compelling evidence for inflation came from incredibly precise maps of the cosmic microwave background. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and most recently the Planck mission have measured the faint temperature variations in this ancient light. These tiny fluctuations on the order of 1 part in 100,000 are the imprint of quantum seeds' minuscule density variations that were stretched to astronomical sizes during inflation. These became the gravitational seeds around which all the future structure of the universe, galaxies and clusters of galaxies, would eventually form. Without these quantum whispers amplified by inflation, the cosmos would be a vast, empty, and featureless void. The hunt for even more direct evidence continues with the pursuit of primordial gravitational waves. Inflation's violent expansion should have sent ripples through the very fabric of spacetime itself. Detecting these waves would be like listening to the echo of the Big Bang's first shout, providing irrefutable proof of inflation's chaotic birth. While acclaimed detection by the BICEP 2 telescope in 2014 turned out to be interference from cosmic dust, the search is far from over. New, more sensitive experiments are being planned, aiming to tune into the deepest frequencies of the universe and perhaps finally hear the resonating hum of our cosmic dawn. While the idea of a single, definitive beginning is compelling, another theory proposes our universe's birth was not a unique event but merely one chapter in an endless cosmic story. This is the cyclic model, a vision of a universe without a true beginning or end, where expansion and contraction follow one another in an eternal, rhythmic dance. Imagine a cosmic heartbeat where each beat is a complete universe, from a hot, dense Big Bang to a possible future collapse into a big crunch, only to rebound again into a new expansion. This model reimagines the ultimate fate of the cosmos not as a cold, lonely fade into darkness, but as a perpetual cycle of death and rebirth. This concept elegantly sidesteps the perplexing question of an absolute beginning. Instead of a singularity where physics breaks down, each cycle emerges from the collapse of the previous one. In some versions, the universe expands to a maximum size due to dark energy, then contracts under its own gravity in a big crunch, recycling all matter and energy back into a hot, dense state to begin anew. Other versions incorporate a big bounce, where the collapse reverses at a quantum scale before reaching a true singularity, propelled into a new expansion by repulsive quantum forces. This offers a profoundly different perspective on time itself, suggesting our entire cosmic history is just one iteration in an infinite sequence with no true start and no final end. The modern incarnation of this ancient idea is deeply intertwined with string theory and its extension, brain cosmology. In this framework, our entire universe might be a three-dimensional membrane or brain floating within a higher dimensional reality. The Big Bang, in this view, could have been triggered by a collision between our brain and another parallel universe brain. These collisions would inject immense energy into our dimensional plane, fueling an expansion we experience as a hot Big Bang. After the collision, the brains move apart, our universe expands and cools, and eventually the attractive force between them draws them back together for another collision, resetting the cycle. This transforms the cosmic story from a linear narrative into an epic, repeating interaction between worlds we cannot see. This model offers its own fascinating explanations for the properties we observe. The incredible smoothness and flatness of our universe could be a natural consequence of these cyclic events. Each cataclysmic collision and subsequent expansion would stretch and flatten the cosmos, erasing the wrinkles of the previous cycle. The tiny quantum fluctuations that seeded all galaxies could be imprinted on the universe from the energy of the brain collision itself, providing an alternative origin story for the large-scale structure we see today. It paints a picture where the universe doesn't need a precise, inexplicable set of initial conditions. It simply inherits a refined state from the thermodynamic processes of the previous cycle. The appeal of a cyclic universe is undeniable, offering a sense of eternal continuity that a single birth universe lacks. However, it faces significant challenges. A major hurdle is the second law of thermodynamics, which states that entropy or disorder always increases. If the universe has already undergone an infinite number of cycles, entropy should have reached its maximum value by now, resulting in a featureless, high-entropy state we clearly do not observe. This is known as the entropy problem. Proponents of the model work on solutions, suggesting that the expansion in each cycle is so vast that it effectively dilutes entropy, resetting the clock and allowing for new structure to form each time. The search for evidence is even more abstract. Some theories suggest a cyclic model might leave a specific pattern in the cosmic microwave background polarization or gravitational waves, a faint signature of a pre-Big Bang event. While still speculative, the cyclic model expands our imagination of what is possible, challenging us to consider that our entire cosmos might be just one episode in a grand multiverse-scale saga without end. But if the cyclical model challenges our notion of a beginning, our next theory completely upends our understanding of reality's very dimensions. This is the holographic principle, a concept so profound and counterintuitive that it suggests everything we perceive in our three-dimensional world, every galaxy, every person, every thought, might actually be a complex projection of information encoded on a distant two-dimensional surface. The roots of this astonishing idea don't come from cosmology, but from the most enigmatic objects in the universe, black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, which is a measure of its information content or disorder, is not proportional to its volume as you might expect for a three-dimensional object. Instead, it's proportional to the surface area of its event horizon. This was a huge clue that all the information describing everything that ever fell into the black hole might not be lost inside its volume, but could instead be smeared across its two-dimensional boundary. This idea was solidified by Stephen Hawking's work showing that black holes aren't completely black. They slowly radiate energy and evaporate over astronomical timescales. This created a major puzzle known as the black hole information paradox. If a black hole evaporates and disappears, what happens to all the information about the stars, gas, and matter that fell into it? The fundamental laws of quantum mechanics state that information can never be truly destroyed. The holographic principle offers a stunning solution. The information isn't lost because it was never actually inside the black hole to begin with. It was always stored on the event horizon, encoded in minuscule Planck-sized pixels, much like the pixels on a television screen or the data on a credit card hologram. The three-dimensional interior we imagine is just a representation of that data, a projection that appears real to any observer who might fall in. The principle was taken to its ultimate conclusion by physicist Juan Maldaisner in 1997. Using the mathematical framework of string theory, he found a concrete, albeit theoretical, example of holography in action. He described a universe with a specific type of anti-gravity, known as anti-de Sitter space. In this model, a full description of the physics happening within the volume of that universe is completely equivalent to a quantum theory operating on its lower dimensional boundary. It's as if the entire bustling, three-dimensional cosmos we experience is like a movie being projected from the data on a vast cosmic film reel that exists at the edge of everything. The physics on the surface and the physics in the volume are two different descriptions of the same reality. One is not more real than the other. This has earth-shattering implications for our understanding of space and time. If the holographic principle is correct, then space itself is not fundamental. It's an emergent property, something that arises from the complex interactions of quantum information. Time might also be emergent. This could be a crucial step toward reconciling Einstein's theory of gravity, which describes the smooth curvature of space-time, with quantum mechanics, which governs the frenetic behavior of the very small. In this view, gravity itself might not be a fundamental force, but a consequence of the quantum entanglement of all those bits of information on the boundary. We are, in a very literal sense, living in a universe-sized illusion, a hologram of staggering complexity where the information for every event, every particle, and every force is written on the fabric of the cosmic horizon. Yet for all its explanatory power, inflation introduces a truly staggering possibility, one that redefines the very meaning of reality. If space can expand exponentially once, what's to stop it from doing so again, in regions far beyond our observable horizon? This leads us to one of the most profound and controversial ideas in all of cosmology, the multiverse. The theory suggests our entire cosmos, with its specific laws and constants, might be just one bubble in a vast, infinite, and ever-growing cosmic foam, where countless other universes exist with completely different rules. We are not just living in a universe, but within a multiverse. This concept emerges naturally from the theory of eternal inflation. The idea is that the repulsive gravity driving inflation doesn't shut off everywhere at once. In our region of space, the inflation field decayed, its energy converting into the hot soup of particles for our Big Bang. But according to quantum physics, this decay is a probabilistic process. In other regions, the inflation field continues to dominate, causing space to expand at a mind-boggling rate. In these still inflating areas, quantum fluctuations can cause new patches to randomly decay, each one spawning its own separate bubble universe with its own localized Big Bang. Our entire observable universe is just one such bubble in an eternally inflating meta-universe where the process has no end, continuously birthing new cosmic domains forever. But the multiverse isn't a single idea, it's a spectrum of concepts. Another compelling version comes not from cosmology, but from the strange world of quantum mechanics, the many worlds interpretation. Proposed by Hugh Everett in the 1950s, it suggests that every time a quantum event occurs with multiple possible outcomes, the universe doesn't choose one. Instead, it splits into multiple branches, each one representing a different outcome. Did that radioactive atom decay or not? In one universe, it did. In another, it did not. This isn't just about atoms. Every decision, every random event would spawn new timelines, creating a constantly branching tree of reality where every possibility is realized somewhere. In this view, the multiverse is an ever-expanding tapestry of alternate histories and futures. The most powerful implication of the multiverse is how it potentially solves the mystery of fine-tuning. Our universe appears miraculously crafted for life. If the strength of gravity were slightly stronger, stars would burn out too quickly, slightly weaker, and no stars would form at all. The cosmological constant, which drives the universe's expansion, is fine-tuned to an accuracy of 1 part in 10 to the 120, a number so incomprehensibly precise it has been called the most embarrassing number in physics. The multiverse offers an elegant, if humbling, explanation. There's nothing special about our universe's settings. With an infinite number of universes, each with random physical constants, it's no surprise that we find ourselves in one of the rare habitable ones. We are the winners of a cosmic lottery we didn't even know we were playing. Of course, such a vast concept is not without its critics. A major challenge is testability. If these other universes are forever beyond our causal reach, separated by unimaginably vast stretches of eternally inflating space, can we ever gather empirical evidence to support their existence? Some physicists argue this moves the idea from science to philosophy. Yet, proponents search for possible signatures. Perhaps our bubble universe collided with another in the distant past, leaving a bruise in the pattern of the cosmic microwave background. Maybe the specific distribution of galaxies across the sky holds a clue. While definitive proof remains elusive, the multiverse persists because it provides compelling, naturalistic answers to questions that otherwise point to cosmic coincidence or something beyond physics. It forces us to confront the possibility that everything we know is just a small part of a reality far grander and more bizarre than we ever imagined. Yet for all its grandeur, the multiverse concept builds upon a foundation that is still under construction, the quest for a complete theory of quantum gravity. This brings us to one of the most mathematically sophisticated and ambitious frameworks ever devised, string theory. This approach doesn't just tweak our current understanding of the universe, it proposes a fundamental rewrite of reality's basic ingredients. Instead of point-like, zero-dimensional particles, string theory suggests that at the heart of all matter and energy are unimaginably tiny, vibrating loops of energy strings. And in this elegant vision, the entire cosmic symphony, from the birth of the universe to the formation of galaxies, is played out through the resonant frequencies of these strings. The core idea is both simple and profound. Imagine a violin string. Depending on how it's vibrating, it produces different notes, a G, a D, an A. In string theory, every single particle in the universe is akin to a different musical note played on a fundamental string. An electron isn't a tiny dot, it's a string vibrating at one specific frequency. A photon of light is the same type of string, just vibrating at a different frequency. A quark is yet another note. In this framework, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, are not separate entities but simply different harmonies arising from the same vibrational ensemble. This unification is the theory's holy grail, offering the potential to describe all of nature's forces within a single, elegant mathematical structure. However, this beautiful mathematical harmony comes with a stunning and necessary requirement: extra dimensions of space. For the equations of string theory to work consistently, they demand that the universe has more than the three spatial dimensions we experience. The most popular version, superstring theory, requires 10 dimensions, 9 of space and 1 of time. So where are these other 6 dimensions? The theory proposes they are compactified or curled up into an infinitesimally small, intricate shape at every single point in our familiar three-dimensional space. To understand this, picture a long, thin garden hose. From a distance, it appears as a simple one-dimensional line. But if you were an ant crawling on its surface, you'd discover a second dimension curled around its circumference. In the same way, at every point in our cosmos, there could be 6 extra dimensions curled into a complex geometric form known as a Calabi-Yau manifold. The specific way these dimensions are folded determines the vibrational patterns of the strings, which in turn dictates the laws of physics, the masses of particles, and the strengths of forces in that universe. This leads directly to one of string theory's most controversial contributions to cosmology: the landscape of possible vacuum states. The mathematics of string theory doesn't predict one unique set of physical laws. Instead, it suggests a colossal number of possible stable configurations for those compactified dimensions. Estimates range from 10 to the 500 up to an almost unimaginable 10 to the 2072 different possible universes, each with its own unique laws and constants. This vast landscape provides a potential physical mechanism for the multiverse. Our universe, with its specific, life-permitting laws, might simply be one valley in this sprawling cosmic landscape, a single stable configuration that emerged from the fiery chaos of the beginning. The fine-tuning we observe may not be fine-tuning at all, but merely the outcome of a random selection process on a scale beyond human comprehension. When applied to the universe's first moments, string theory offers a radical alternative to the traditional singularity of the Big Bang. The theory suggests that as we rewind time to that moment of infinite density, the physics of strings would take over from the classical physics of point particles, smoothing out the singularity. One compelling model is the ekpyrotic universe, which envisions our Big Bang as a colossal collision between two of these higher dimensional brains in an 11-dimensional bulk space. This collision would transfer immense energy into our three-dimensional world, heating it to incredible temperatures and initiating the expansion we see, all without ever passing through a state of infinite density. This provides a potential beginning that is not a true singularity but a transition from a previous phase, a concept that is far more palatable to physicists. Despite its mathematical beauty and explanatory power, string theory remains just that, a theory. It has yet to make a single testable prediction that can be verified through experiment, and the energy scales required to probe these tiny strings are far beyond the reach of any particle accelerator we could ever hope to build. Critics argue it's more philosophy than physics, a fascinating but ultimately untestable set of ideas. Yet for many, its power to elegantly weave gravity into the quantum tapestry and provide a potential framework for understanding the very origin of spacetime itself makes it an irresistible and perhaps necessary path to pursue in our quest to understand the cosmos's first breath. While string theory adds extra dimensions to reality, another brilliant group of physicists asked a completely different question. What if we don't need to change the dimensions we have, but instead need to change our understanding of what they're made of? This is the heart of loop quantum gravity, or LQG, a bold and elegant alternative that seeks to describe the fabric of spacetime not as a smooth, continuous backdrop, but as a tapestry woven from individual, discrete threads. It's a theory that doesn't try to unify all forces at once, but instead focuses on a single, monumental task, applying the rules of quantum mechanics directly to gravity itself by quantizing the very stage upon which the cosmic play unfolds. The core philosophy of LQG is profoundly different from string theory. Instead of proposing new, unseeable objects like strings or brains, it takes Einstein's theory of general relativity, which describes gravity as the curvature of spacetime and makes it quantum. In the quantum world, everything is granular. Energy, light, and matter all come in tiny, indivisible packets called quanta. Loop quantum gravity argues that spacetime itself must also be quantized. It suggests that space is not infinitely divisible. You cannot keep cutting it into smaller and smaller pieces forever. At a fundamental level, space is made of finite, tiny building blocks. Imagine a piece of fabric. To the naked eye, it looks smooth and continuous, but if you look closely with a powerful magnifying glass, you see it's actually woven from individual, interlocking threads. Loop quantum gravity proposes that the universe itself is such a fabric, with a finite, woven structure at the smallest possible scale. This granular structure is described by two key concepts: spin networks and spin foam. A spin network represents quantum space. Picture a vast, ever-changing web where the lines of the web are not in space, they are space. Each intersection point or node represents a tiny volume of space, and the links between them represent the surfaces that separate these volumes. The entire network is buzzing with quantum activity, with each link labeled with a number related to quantum spin. This isn't the spin of a planet, it's a fundamental quantum property that defines the area of the surface. Now, to introduce time, we animate this network. As time passes, the network evolves, with nodes appearing and links changing. This evolution creates a four-dimensional structure, three of space, one of time, that physicists call a spin foam. It's a frothy, dynamic substance that constitutes the very foundation of reality, with bubbles of spacetime constantly forming and dissolving at the Planck scale. This radical reimagining of spacetime's structure provides a stunning solution to the most troubling aspect of the Big Bang, the initial singularity. In Einstein's classical theory, the Big Bang is a point of infinite density and temperature where the laws of physics completely break down. It's a place where mathematics fails, a place we cannot describe. Loop quantum gravity removes this problem entirely. Because space is quantized, there is a smallest possible volume. You cannot crush the universe into a point of zero size. There is a fundamental limit to how small it can get. As we rewind time, the universe gets denser and hotter, but instead of collapsing into a true singularity, it reaches a point where the repulsive force of quantum gravity becomes overwhelming. This quantum pressure acts like a cosmic trampoline, causing the collapsing universe to rebound in a tremendous, explosive, big bounce. This transforms our cosmic origin story from a one-time beginning into a potential cycle. Our universe may not have been born from nothing, but from the collapse of a previous cosmic phase. The Big Bang was not the absolute beginning, but the moment of this great rebound. This provides a breathtakingly beautiful and physically plausible narrative, a universe that cycles through expansions and contractions, possibly for eternity. Each bounce would effectively reset the cosmic clock, erasing much of the information from the previous cycle, but potentially leaving subtle imprints. The incredible smoothness and flatness we observe today could be a natural result of the immense forces involved in the bounce, which would have stretched and ironed out any wrinkles from the prior universe. The theory also makes a fascinating prediction about the nature of reality at its smallest scale. That time itself may not be fundamental. In the spin foam description, time emerges from the relationships between the events in the network. There is no master clock ticking outside the universe. The flow of time we experience is a macroscopic consequence of the underlying quantum interactions. This challenges our most basic intuition about the nature of existence and aligns with what some philosophers have argued for centuries. Like all great theories of quantum gravity, LQG currently exists in the realm of profound prediction rather than direct observation. The energy required to probe the Planck scale is astronomically beyond our reach. However, the theory does offer potential pathways for testing. Some models suggest that the granular structure of space could subtly affect the propagation of very high-energy light across the universe. If photons of different energies generated simultaneously in a gamma-ray burst were to arrive at our telescopes at slightly different times due to bumping against the granular structure of spacetime, it could be a detectable signature. While such evidence has yet to be conclusively found, the very fact that the theory offers these kinds of testable predictions keeps it at the forefront of theoretical physics, representing a completely different, yet equally compelling, vision for how our universe began. Now, let's venture into a theory that feels almost like science fiction, yet is grounded in the sophisticated mathematics of string theory. This is the ekpyrotic universe model, a concept that reimagines our cosmic genesis not as an explosion from a single point, but as a colossal, universe-shattering collision between two worlds in a higher dimensional reality. The name itself, ekpyrotic, comes from the ancient Greek word for conflagration or out of fire, and it paints a dramatically different picture of the beginning. Instead of a singularity, the theory proposes that our three-dimensional universe is actually a membrane or brain, existing within a higher dimensional space often called the bulk. In this vast, unseen arena, another similar brain could be floating parallel to our own. Picture two enormous, perfectly flat sheets of paper floating silently and motionless in a vast, dark room. Now, imagine they are drawn slowly together by an invisible force until they smash into each other. That cataclysmic impact, that moment of unimaginable energy release, is what the ekpyrotic model identifies as our Big Bang. The immense heat and density generated from that collision are what we now interpret as the starting point of our cosmic timeline. It wasn't an explosion in space, but a violent event that created the hot, expanding state of our specific brain. This model offers a compelling and elegant alternative explanation for the very same cosmic puzzles that inflation was designed to solve, namely the horizon and flatness problems. How did the universe become so incredibly uniform? In the ekpyrotic scenario, the two colliding brains can be naturally flat and smooth over incredibly vast scales. Since the collision happens almost simultaneously across their entire surfaces, it imparts that same uniformity to the newborn universe. There's no need for a faster-than-light inflationary period to smooth things out because the initial conditions, the brains themselves, were already smooth. The flatness of our universe is also a natural inheritance. The brains are theorized to be fundamentally flat structures within the higher dimensional bulk, so the universe they create through collision would also be flat, perfectly balancing the expansion rate and the pull of gravity. Furthermore, the ekpyrotic model provides its own mechanism for generating the seeds of all cosmic structure. Just as in inflation, quantum mechanics plays the crucial role. But here, the quantum fluctuations aren't in an inflating field. They are tiny, random ripples in the positions of the two brains themselves as they approach each other. Some regions of the brains collide a fraction of a second earlier than others, and some hit with slightly more energy. When these ripples are stretched across the expanding post-collision universe, they translate into the tiny variations in density that gravity would later use to build galaxies, stars, and ultimately us. This process can produce a pattern of temperature fluctuations in the cosmic microwave background that is nearly identical to that predicted by inflation, making it a formidable and sophisticated competitor in explaining our origins. One of the most intriguing aspects of this theory is its connection to a cyclical view of the cosmos. The ekpyrotic model can be part of a grander cyclical narrative where the brains undergo repeated collisions. After smashing together and creating a new universe, they might spring apart, only to be drawn together again by a mysterious force across eons, setting the stage for the next cosmic rebirth in an endless cycle of creation and destruction. This elegant framework sidesteps the thorny issue of an absolute beginning, suggesting our universe is just the latest episode in an eternal cosmic saga, with its birth written in the fire of a collision between worlds we can scarcely imagine. Now, let's turn to a theory that tackles the problem of the beginning from an entirely different angle, one that seeks to erase the problem of a starting point altogether. This is the no-boundary proposal, a deeply elegant and profoundly conceptual idea co-developed by the legendary Stephen Hawking and physicist James Hartle. Their radical proposition was that the universe is entirely self-contained. It has no boundary, no edge, and crucially, no beginning in time as we traditionally understand it. There was no moment of creation, no singularity where the laws of physics break down. Instead, the universe just is in a complete and seamless whole. To wrap your mind around this, you need to think about geometry, and the best analogy is right beneath our feet. Think about the planet Earth. You can travel across its surface in any direction forever, and you will never encounter an edge. The surface is finite in area, yet it has no boundary. Now ask yourself, where does the surface of the Earth begin? This question doesn't make sense. There is no north of the North Pole. The North Pole is a point on the globe, but it isn't a boundary. It's simply a place where our usual definition of latitude breaks down. Hawking and Hartle proposed that the universe in its entirety is like this. Time, especially as we approach the beginning, behaves more like a dimension of space, creating a smooth, curved, four-dimensional shape without any sharp edges or starting points. The Big Bang becomes the North Pole of time, not an explosion from nothing, but a point we can identify on a seamless, closed surface. This incredible smoothing out of the Big Bang singularity is made possible by a fascinating mathematical trick, the use of imaginary time. Don't let the name fool you. It's a very real mathematical concept. In simple terms, it involves treating the time dimension in the extreme conditions of the very early universe as if it were a fourth dimension of space. This transformation, a Wick rotation, allows physicists to work with equations where the singularity simply vanishes, replaced by a smooth, curved geometry. It's like being able to round off the tip of a sharp pencil perfectly, removing the point where it would tear a piece of paper. In this imaginary time domain, the universe is a perfectly smooth, closed surface with no boundaries, making the question, what happened before the Big Bang? As meaningless as asking what is north of the North Pole, the no-boundary proposal is fundamentally a quantum gravity concept. It describes the universe not as a single classical history, but as a superposition of all possible histories, just as a quantum particle exists in a cloud of possible locations. The most probable history for our universe, according to this model, is the one that smoothly curves from nothing to the expansive cosmos we see today. This provides a natural explanation for why the universe started in such a highly ordered, low-entropy state, addressing a deep mystery in cosmology. It wasn't a miraculous starting condition. It was the only way a universe with no boundary could emerge from the quantum foam. The initial smoothness and flatness were baked into its very geometry from the outset. Of course, such a mind-bending idea is not without its challenges and philosophical implications. A major question is what this nothing really is. In the no-boundary proposal, it's not a literal void, but the simplest possible quantum state of fluctuation in the underlying fields of reality. The universe would have spontaneously appeared through a process of quantum tunneling, not from some other pre-existing space, but from a state where the very concepts of space and time have no meaning. It represents the ultimate free lunch, the emergence of everything from a set of self-consistent physical laws that require no external cause or creator. It presents a universe that is its own reason for being, a self-explanatory entity governed entirely by the cold, beautiful, and unforgiving laws of quantum mechanics and gravity. But if the universe truly began from a self-contained, no-boundary state, what if its story doesn't end there? What if the end is also a beginning? This leads us to a theory so elegant and audacious that it could only come from a mind like Sir Roger Penrose's. It's called Conformal Cyclic Cosmology, or CCC, and it proposes a breathtakingly beautiful vision of eternity. Our universe is not the first, nor will it be the last, but merely one in an infinite series of cycles, each one's death giving birth to the next in an unending cosmic loop. Penrose's genius was in finding a profound connection between two seemingly opposite extremes: the universe's hot, dense beginning and its cold, empty end. Current models suggest our cosmos will continue expanding forever, driven by dark energy. Over trillions upon trillions of years, all stars will burn out, black holes will slowly evaporate via Hawking radiation, and matter itself will eventually decay. The universe will approach a state of maximum entropy, a dark, frigid, and nearly featureless void, where the temperature effectively drops to absolute zero, and no events of any significance can ever occur again. This heat death has long been seen as the final, depressing conclusion to everything. But Penrose asked a revolutionary question: what does this lifeless, empty, cold future state actually look like to the laws of physics? His astonishing answer is that it becomes indistinguishable from the hot, dense Big Bang. This is the core of conformal cyclic cosmology. The mathematics of conformal geometry allows physicists to rescale distances and times, effectively zooming out on the universe. When you apply this rescaling to the infinitely stretched, empty future, all the massive particles and complex structures vanish from the picture. What remains is a smooth, energetic, low-entropy state that mathematically looks identical to the high-energy, low-entropy singularity from which our universe began. In this conformally rescaled view, the end of time in one cycle becomes the beginning of time in the next. The universe forgets its scale, and a cold, dead expanse is reborn as a hot, dense fireball, ready to explode into a new cycle of creation. This radical idea provides a potential explanation for one of the most perplexing modern mysteries in cosmology: strange, large-scale anomalies found in the cosmic microwave background. The CMB is remarkably uniform, but not perfectly so. Detailed maps from the Planck satellite have revealed several large, faint, circular patterns of lower-than-average temperature, regions where the universe appears suspiciously smooth. These are known as Hawking points, and Penrose and his collaborators propose they are nothing less than the imprints of supermassive black holes from a previous cosmic con. As the previous universe met its end and underwent conformal rescaling, the immense gravitational energy and Hawking radiation from the evaporation of these colossal objects could have been imprinted onto the fabric of spacetime itself, creating faint, circular ripples that were then stretched to cosmic sizes during our own universe's inflation. These are the cosmic bruises, the ghostly echoes of a universe that existed before our own. The implications of conformal cyclic cosmology are staggering. It suggests that the arrow of time, the reason we remember the past and not the future, is not a fundamental property of the universe but a feature unique to each cycle. Entropy increases within each con, driving the complexity that allows for stars, planets, and life. But at the moment of crossover between cycles, entropy is effectively reset to zero, allowing for a new beginning. The universe is not just eternal, it is immortal, constantly recycling itself in a dance of death and rebirth that has no beginning and will have no end. Every particle in your body, every star in the sky, has likely existed in countless forms across countless cycles, participating in an infinite cosmic story where every ending is merely a prelude to a new and spectacular beginning. Yet as we marvel at these grand cosmological cycles, a more intimate and perhaps more profound question emerges. Why does our universe seem so perfectly tailored for our existence? This leads us to the anthropic principle, a concept that bridges the gap between the vast, impersonal cosmos and the delicate conditions necessary for life. At its heart, this principle suggests that the universe must be compatible with the conscious life that observes it. We shouldn't be surprised to find ourselves in a universe with the right properties for our existence, because in a universe without those properties, we wouldn't be here to ask the question in the first place. It's a statement that feels almost self-evident, yet its implications for cosmology are truly revolutionary. This idea comes in two distinct flavors, each with its own depth and philosophical weight. The weak anthropic principle is the more conservative version, essentially a selection effect. It notes that the physical constants of our universe, things like the strength of gravity, the mass of an electron, or the force that holds atomic nuclei together, appear to be exquisitely fine-tuned for life. If any of these values were even slightly different, the consequences would be catastrophic. A stronger gravitational constant would cause stars to burn out in a cosmic blink. A weaker force binding atoms would prevent the formation of any complex elements. The weak principle simply states that we observe these precise values because we exist in a universe where such values allow for observers. We are, in a sense, cosmic lottery winners, but it doesn't explain why this particular winning ticket was drawn. The strong anthropic principle takes a much more dramatic leap. It proposes that the universe must have those properties that allow life to develop at some stage in its history. This version suggests there is something fundamental about the connection between consciousness and the cosmos, that the laws of physics are not random but are in some way necessitated by the requirement to produce conscious observers. To some, this hints at a form of teleology, a purpose or direction woven into the fabric of reality itself. It's an idea that resonates with certain philosophical and theological viewpoints, suggesting the universe was in some sense meant to be inhabited. The anthropic principle finds its most powerful application as a potential solution to the puzzle of fine-tuning. The precise values of the constants of nature appear to be incredibly unlikely. The cosmological constant, which drives the acceleration of the universe's expansion, is fine-tuned to an accuracy of 1 part in 10 to the power of 120. That's a number so unimaginably precise it has been called the most outrageous number in all of physics. The anthropic principle, particularly when paired with the multiverse concept, offers a naturalistic explanation. If there are countless universes, a vast multiverse, each with its own random set of physical laws and constants, then it is no longer surprising that we find ourselves in one of the rare, bio-friendly ones. We are simply living in the neighborhood that permits life, while most of the multiverse may be stillborn, empty, or utterly bizarre. This line of thinking transforms the landscape of theoretical physics. It doesn't just explain why our universe is the way it is. It changes what we should expect from a fundamental theory. Instead of a theory that predicts one unique set of constants, we might need a theory that predicts a vast landscape of possibilities, exactly what string theory appears to offer with its 10 to the 500 possible vacuum states. Our universe becomes one point in this colossal cosmic landscape. This shifts the goal of physics from explaining why our constants have their specific values to explaining the mechanism that generates the multiverse and the probability distribution of constants within it. Naturally, the anthropic principle is not without its fierce critics. Some physicists argue it is a cop-out, a surrender of the scientific quest for a deeper explanation. They fear it could be used to explain anything, potentially halting further investigation into why the constants have their values. Instead of accepting anthropic reasoning, they hold out hope for a deeper, more fundamental theory that would mathematically derive our constants from first principles, making their life-permitting values a necessity, not a coincidence. The debate often hinges on whether one finds the multiverse a compelling concept or an untestable retreat from empirical science. The philosophical implications are equally profound, touching on age-old questions about our place in the cosmos. Does the anthropic principle suggest a universe that is somehow biased towards life and mind? Or does it simply highlight our own incredible luck amidst a largely hostile and empty multiverse? It forces us to confront the nature of existence itself, blurring the line between the observer and the observed, and suggesting that our very presence might be an integral part of the cosmic story we are trying to tell. But perhaps the most radical idea of all is that our entire universe, in all its vastness and complexity, could be the result of a random subatomic event, a quantum fluctuation on the grandest possible scale. This theory pulls from one of the most well-tested and bizarre aspects of modern physics, the fact that empty space is not truly empty. According to quantum field theory, what we call a vacuum is actually a seething, bubbling cauldron of activity. At the tiniest scales, pairs of virtual particles and antiparticles constantly blink into and out of existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and paying the energy back. This isn't just theoretical, it's a verified phenomenon with real-world effects like the Casimir force, where two metal plates placed extremely close together in a vacuum are pushed together by the pressure of these virtual particles popping off outside them. This reveals a profound truth about the nature of reality. Nothing is unstable. A perfect vacuum is not a state of serene nothingness but the lowest possible energy state, and like a ball resting at the bottom of a valley, it can still experience random quantum jitters. The theory of quantum fluctuation origins takes this idea to its ultimate conclusion. It proposes that our universe is one such fluctuation, not a pair of particles, but an entire cosmos spontaneously appearing from the quantum foam. In this view, the Big Bang wasn't a singular explosion from a pre-existing point, but the rapid expansion of a bubble of space-time that tunneled into existence from literally nothing. It's the ultimate free lunch, the universe borrowing energy from the vacuum of a larger meta-reality, or perhaps from nothing at all, with the positive energy of all the matter and radiation being perfectly balanced by the negative gravitational energy of the cosmos, resulting in a net energy of zero. Visualizing this is a challenge, but imagine the surface of a perfectly still pond. That surface represents the void. Now, imagine a single bubble forming at the bottom and rapidly rising to the surface. Our universe is that bubble. From the perspective of the bubble, it has a beginning, a history, and a future. But from the perspective of the pond, it was just a temporary fluctuation. The laws of quantum mechanics allow for such improbable events because, given enough time or in a timeless void, enough probability, even the most unlikely event will eventually occur. The inflation that followed would then be the mechanism that stretched this tiny quantum bubble into the macroscopic universe we inhabit today, freezing that initial fluctuation into the permanent structure of reality. This idea elegantly bridges the quantum world with the cosmic. suggesting that the same rules governing the behavior of electrons and photons also govern the origin of everything. It provides a natural, physical mechanism for the universe's creation that doesn't require any external cause or prime mover. It simply emerges from the inherent unpredictability and dynamism woven into the fabric of reality at its most fundamental level. The question, what was before the Big Bang, might be as meaningless as asking what is north of the North Pole. In this framework, time itself may have begun with the fluctuation, making the concept of a before a logical impossibility. Yet as we ponder the universe springing from a quantum fluctuation, we encounter a theory that is perhaps the most provocative of all, one that asks whether the very reality we perceive is not fundamental but constructed. This is the simulation hypothesis, the startling idea that our entire universe, with all its galaxies, history, and conscious experience, might not be the base level of reality, but an incredibly sophisticated simulation, a kind of cosmic video game running on the computer of a vastly advanced civilization. The roots of this idea stretch back to ancient philosophy. Plato's allegory of the cave painted a picture of humans mistaking shadows on a wall for reality itself. Centuries later, René Descartes pondered how we could truly know that our senses aren't being systematically deceived by an evil demon. The modern simulation hypothesis updates this ancient skepticism with the language of computer science. If a future civilization were to achieve a level of computing power far beyond our own, capable of simulating not just weather patterns or galaxies, but conscious minds themselves, how could we, as potential simulated beings, ever tell the difference? The universe, with its finite resolution and computable laws, begins to look less like a fundamental reality and more like a perfectly rendered simulation operating on an unfathomable hardware. The argument was famously popularized by philosopher Nick Bostrom in 2003. He broke it down into a logical trilemma, suggesting that at least one of three propositions must be true. First, that almost all civilizations at our level of development go extinct before achieving advanced simulation technology. Second, that almost all advanced civilizations lose interest in creating such ancestor simulations. Or third, that we are almost certainly living in a simulation right now. If you believe that a future civilization could and would choose to run vast numbers of such simulations for historical or scientific research, then the number of simulated minds would dwarf the number of biological ones. Therefore, statistically speaking, any randomly selected conscious being, including you, is far more likely to be one of the simulated ones. It's a probabilistic argument that is as elegant as it is unsettling. Some physicists have looked for potential experimental tests, ways to uncover a possible signature in the very code of our reality. One idea is to search for evidence of a finite resolution to the universe. Just as a digital image breaks down into pixels when you zoom in far enough, space-time itself might have a fundamental graininess at the incredibly small Planck scale. If our universe is a simulation, this pixelation might manifest as a limit to how much energy a particle can have, something we might detect in the highest energy cosmic rays arriving from deep space. Others have suggested looking for computational shortcuts or rounding errors in the laws of physics. A simulator might use approximations in areas we rarely observe to save on processing power, perhaps leaving subtle inconsistencies in the constants of nature or in the outcomes of complex quantum experiments. Finding such a glitch in the matrix would be the ultimate scientific discovery, revealing that our cosmos is a programmed construct. The hypothesis forces us to confront deep questions about the nature of consciousness and reality. If we are in a simulation, does that make our experiences, our loves, and our struggles any less real? Or does it simply mean that reality operates on a substrate of information processing rather than material substance? It blurs the line between physics and metaphysics, challenging us to consider that the laws of nature might not be fundamental laws at all, but simply the rules of the simulation's engine, lines of code written by programmers whose motives we cannot begin to comprehend. Whether you find the idea a fascinating thought experiment or a likely truth, it remains a powerful testament to humanity's drive to question absolutely everything, even the very nature of existence itself. While many theories explore quantum origins or extra dimensions, another compelling idea suggests we've been overlooking a fundamental force that shapes the cosmos on the grandest scales. This is the plasma universe theory, also known as plasma cosmology, a radically different vision where the primary architect of the universe isn't gravity but electromagnetism. In this framework, the vast dynamic structures we see, galaxies, nebulas, and even the large-scale web of the cosmos, are not sculpted by gravity alone over billions of years, but are formed and organized by powerful electric currents flowing through the conductive medium of space itself, plasma. Plasma is often called the fourth state of matter, an ionized gas where electrons have been stripped from atoms, creating a sea of charged particles that is highly responsive to electromagnetic fields. It's not some exotic substance, it's actually the most common form of visible matter in the universe, making up an estimated 99% of all stars, including our Sun, and filling the vast spaces between them. Proponents of this theory, like Nobel laureate Hans Alfvén, argued that because plasma is electrically conductive, it can carry currents across light years of space, forming immense circuits that generate their own magnetic fields. These currents, pinched by their own magnetic forces, can twist and contort into long, filamentary structures that we observe everywhere, from the tendrils of a nearby nebula to the colossal web of galaxy clusters. This perspective directly challenges key aspects of the standard Big Bang model. Instead of a universe born from a single explosive event and evolving primarily under gravity, the plasma universe envisions a cosmos that is eternal and infinite, with no definitive beginning or end. Large-scale structures aren't just the slow result of gravitational collapse acting on dark matter. They are the visible manifestations of cosmic-scale electrical phenomena. Galaxies might not be isolated islands held together by gravity, but rather nodes in a vast, interconnected galactic circuit, with power flowing along cosmic power lines that are faintly visible as the dark, dusty filaments of the intergalactic medium. The evidence for this electrified view of the cosmos comes from both the lab and the sky. In the 1970s, researchers like Anthony Perrat conducted experiments where they passed electrical currents through plasma in a vacuum chamber. They didn't need supercomputers running gravity simulations. They simply turned up the voltage. Astonishingly, these lab-scale electrical discharges produced self-organizing plasma structures that bore a striking resemblance to galactic formations. The currents naturally formed rotating pinches, double layers, and intricate braided filaments that looked like miniature versions of spiral galaxies and galactic jets. This suggests that the beautiful spiral arms of a galaxy might not be density waves of stars, but the visible signature of vast, rotating Birkeland currents, massive cosmic power lines flowing through and powering the galaxy. When we look out into space with this electromagnetic lens, familiar features start to look very different. The vibrant, sculpted pillars of the Eagle Nebula, often presented as a classic example of star formation through gas and gravity, could instead be interpreted as the product of intense electrical plasma etching. The perfectly aligned and energetic jets screaming from the cores of active galaxies and young stars behave less like ballistic projectiles and more like the focused beams of a cosmic particle accelerator, precisely what you would expect from a powerful electrical discharge. Even the Sun itself might be less a self-contained fusion reactor and more of an electrically powered anode, receiving its energy from currents flowing through the solar system. Of course, the plasma universe theory remains a highly controversial fringe idea within mainstream cosmology. Its greatest weakness, according to critics, is its inability to provide a comprehensive explanation for the cosmic microwave background radiation, the very same afterglow that is a cornerstone of Big Bang cosmology. While plasma physicists can point to the redshift of light from distant galaxies and argue it might be due to mechanisms other than universal expansion, the precise blackbody spectrum and uniform temperature of the CMB present a formidable challenge that the Standard Model explains elegantly. Furthermore, the theory struggles to quantitatively account for the observed abundance of light elements like hydrogen and helium, which the Big Bang nucleosynthesis model predicts with remarkable accuracy. Despite these challenges, the plasma universe theory serves as a vital reminder that our understanding of the cosmos is still evolving. It forces cosmologists to seriously consider the role of electromagnetism, a force that is a billion times stronger than gravity on a cosmic scale. It pushes us to look at the sky not just as a dark void dotted with gravitationally bound objects, but as a dynamic, living circuit, crackling with energy and alive with currents that shape the universe in ways we are only beginning to comprehend. But before the cosmic microwave background sealed the fate of one theory, another compelling idea held sway in the minds of many scientists, offering a vision of the cosmos that was eternal and unchanging. This was the steady-state theory, championed by brilliant minds like Hermann Bondi, Thomas Gold, and Fred Hoyle in the 1940s. In stark contrast to the cataclysmic beginning of the Big Bang, the steady-state model proposed a universe with no start and no end, an infinite and everlasting entity that largely looked the same from any point in space or time. It was a profoundly elegant and philosophical concept, suggesting a cosmos that simply existed without the need for a dramatic creation event. The theory was built on a foundational principle called the perfect cosmological principle. This was an extension of the standard cosmological principle, which states that on large scales, the universe is homogeneous and isotropic. It looks the same in every direction and from every location. The perfect cosmological principle added that it also looks the same at every point in time. Whether you were observing the universe 10 billion years ago or 10 billion years in the future, its overall density and large-scale appearance would remain constant. This was a bold claim that required a truly stable cosmos, but there was an obvious problem. The universe is expanding. As galaxies move apart, the average density of matter in the cosmos should naturally decrease over time. The universe should thin out. To solve this puzzle, the steady-state theorists introduced a truly radical idea, the continuous creation of matter. They proposed that new matter, hydrogen atoms, is spontaneously and constantly being created out of nothingness in the empty voids between galaxies. This wasn't a violent process, but a slow, steady trickle, with perhaps just one new atom popping into existence per cubic kilometer of space every year. This minuscule, ongoing creation would be just enough to exactly compensate for the dilution caused by the expansion, maintaining a perfectly constant average density throughout all eternity. In this view, new galaxies would gradually form from this newly created material, filling in the gaps left by the old ones as they drifted apart, ensuring the overall appearance of the universe never changed. There was no single point of origin. The universe was forever renewing itself. For a time, this was a legitimate competitor to the Big Bang model. It was philosophically appealing to those who were uneasy with the idea of a definite beginning, which to some smacked of a religious creation event. Fred Hoyle, in fact, famously coined the term Big Bang during a 1949 radio broadcast, intending it as a somewhat dismissive label for a theory he found unsatisfactory. The steady-state model was elegant and made specific predictions, but in science, evidence is the ultimate arbiter, and the evidence that eventually emerged was overwhelmingly in favor of a dynamic universe with a hot, dense beginning. The first major blow came with observations of distant radio galaxies. Because light takes time to travel, looking out into space is like looking back in time. Astronomers noticed that radio galaxies were much more common billions of years ago than they are today. This showed that the universe in the past was fundamentally different from the universe now, directly contradicting the perfect cosmological principle's claim of an unchanging cosmos. The universe had an evolutionary history, and it was a history of change. The final, definitive evidence that cemented the Big Bang's victory was the accidental discovery of the cosmic microwave background radiation in 1964. The steady-state theory had no compelling explanation for this all-pervasive, uniform bath of radiation. Its proponents scrambled to find alternatives, suggesting it might be the scattered light from distant stars, but these explanations failed to account for its perfect blackbody spectrum and incredible uniformity. The CMB was exactly the prediction of the Big Bang model, the cooled remnant of the universe's early, hot phase, and it was everywhere. This was the signature of a universe that was not eternally steady, but one that had evolved from a scorching, primordial fireball. While the steady-state theory ultimately fell out of favor, its legacy is far from insignificant. It pushed Big Bang cosmologists to sharpen their own theories and make more precise, testable predictions. The intellectual competition between the two models drove observational cosmology forward at a rapid pace. Furthermore, the idea of an eternal universe has found new life in other forms, like the cyclic or oscillating models we discussed earlier. The steady-state theory remains a fascinating chapter in the history of science, a beautiful and ambitious idea that was ultimately overcome by the clear, consistent voice of observational evidence, reminding us that our understanding of the cosmos is always evolving, guided by the stars themselves. Yet if our universe was born from a star's collapse in a parent cosmos, what if its own black holes are themselves cosmic wombs? This leads us to the extraordinary black hole genesis theory, a concept that proposes every black hole in our universe could be the seed for an entirely new reality, birthing a baby cosmos within its hidden depths. In this breathtaking vision, universes are not isolated entities but exist in a grand, branching hierarchy, with each black hole acting as a tunnel, a one-way gateway from an older universe into a newer one. The foundation for this idea comes from a fascinating look at the mathematics describing a black hole's interior. When an object crosses the event horizon according to Einstein's general relativity, its future is inevitably pulled toward the central singularity, a point of infinite density where our known laws of physics cease to have meaning. But some physicists, like Nikodem Poplawski, have proposed a different outcome using the tools of torsion-based gravity and quantum mechanics. They suggest that the immense gravitational pressure inside a black hole might not lead to a dead-end singularity, but instead trigger a monumental bounce, a reversal of collapse into an explosive expansion. In this scenario, the interior of a black hole doesn't end in a point of destruction, but transforms into the hot, dense beginning of a new universe, expanding into its own set of dimensions, forever separated from the parent cosmos that gave it birth. This theory weaves together several profound threads we've already explored. It resonates deeply with the concept of a big bounce from loop quantum gravity, where a collapsing universe rebounds into a new expansion. It also aligns with the holographic principle, as the information describing everything that fell into the black hole encoded on its two-dimensional event horizon could provide the initial data or quantum seeds for the physical laws and particles within the newborn universe. The parent universe's black hole becomes a conduit transferring information and energy to create an offspring reality whose fundamental constants might be inherited or randomly determined by the specific conditions of its formation. Visualizing this creates a truly cosmic family tree. Our entire universe, with its hundreds of billions of galaxies, each containing billions of stars, could be inside a black hole that formed within a much older, grander universe. And within our own cosmos, every black hole, from the small stellar remnants to the supermassive giants at the hearts of galaxies, could itself contain an entire fledgling universe, forever expanding in its own dimensional realm, completely inaccessible to us. We are not just living in a universe, but within a black hole that is part of an immeasurably vast multiverse, a never-ending chain of cosmic generations where each death in one reality is a birth in another. This provides a stunning and natural explanation for the mystery of fine-tuning. If new universes are constantly being spawned inside black holes, each with slightly different physical constants, a different strength of gravity, a different mass for the electron, then a form of cosmic natural selection could occur. Universes that produce many black holes would, by definition, produce many offspring universes that inherit their successful, black hole-friendly physical laws. Universes that fail to form black holes would be evolutionary dead ends. Over countless generations, this process would naturally select for universes like our own that are exceptionally good at making black holes and stars, which also happen to be the precise conditions that allow for the existence of planets and life. We find ourselves in a universe fine-tuned for life because life is a byproduct of a cosmos fine-tuned for cosmic reproduction. Yet all of these theories, from cosmic collisions to quantum bounces, operate within a framework that assumes a fundamental arrow of time. But what if time itself is not a pre-existing stage upon which the universe plays out, but a property that emerged from a more basic, timeless reality? This brings us to one of the most profound and mind-bending frontiers of cosmology, the very nature of time and the question of what, if anything, could have come before the Big Bang. The word "before" itself is the first hurdle. In our everyday experience, time is a relentless, one-way river flowing from the past through the present and into the future. We instinctively believe that every event must have a cause that came before it. This logic seems to break down at the Big Bang singularity, the point where our current laws of physics predict a beginning to space and time. Asking what happened before the Big Bang might be as nonsensical as asking what is north of the North Pole. Just as the North Pole is the definitive northernmost point on Earth, the Big Bang might represent the definitive beginning of time. There simply is no before in this framework because time itself did not exist. This concept is incredibly difficult to grasp because our brains are hardwired to think in terms of cause and effect within a timeline. But several leading theories in quantum gravity propose that time is not a fundamental ingredient of the universe. Instead, it is an emergent property, a large-scale illusion that arises from the complex interactions of more basic, timeless components. Think of it like the temperature of a gas. A single molecule doesn't have a temperature. Temperature is a collective property that only makes sense when you have a vast number of molecules interacting. In the same way, theories like loop quantum gravity suggest that what we perceive as the flow of time emerges from the quantum relationships between the trillions upon trillions of tiny grains, or quanta, that make up the fabric of space. In this timeless view, the Big Bang was not an event in time, but the moment when time itself crystallized into existence. The universe transitioned from a state where the concept of before and after had no meaning into a state where causality and sequence became the rule. This transition is often described using a mathematical trick called a Wick rotation, where the dimension of time is treated mathematically as if it were a dimension of space when we approach the singularity. This allows physicists to model the Big Bang as a smooth, curved surface like the South Pole on a globe, with no sharp edges, no boundaries, and no definitive starting point. The question of a first cause vanishes because in a state without time, there is no sequencing of events to require one. The implications of this are staggering. It suggests that the ultimate origin of the universe did not happen at a point in time, but was a quantum transition from a state of pure potentiality, where all possible geometries of space-time flickered in a superposition. Our entire cosmic history from the first picosecond to the present day would then be a single, frozen, four-dimensional shape, a block universe where the past, present, and future all equally exist. Our perception of a flowing now is just a neurological artifact, a way our consciousness makes sense of moving through this static structure. In the truest sense, the beginning of the universe is not a moment to be found in the past, but the foundational boundary of reality itself, a feature of the cosmic landscape that we are forever embedded within. This notion of a universe born from a timeless quantum event leads us to one of the most elegant and mind-bending ideas in all of physics, the possibility that the total energy of everything in existence might actually add up to absolutely nothing. This is the null universe hypothesis, a theory that suggests our entire cosmos, in all its vast, complex glory, could be the ultimate free lunch, a fluctuation in the purest state of nothingness that required no input of energy to create. To understand this, we need to think about energy in a very specific way. We see a universe filled with positive energy everywhere we look. The mass of every star, planet, and person is a form of concentrated energy, as described by Einstein's famous equation, E equals mc squared. The light streaming from the sun, the heat from a fire, the motion of the galaxies, all of this represents an enormous amount of positive, active energy. But this is only half of the story. According to Einstein's theory of general relativity, gravity is not just a force, it is the curvature of space-time itself. And this curvature has its own energy, a negative gravitational energy that acts as a kind of cosmic debt. Imagine slowly pulling two massive objects apart against their mutual gravitational attraction. You have to add energy to the system to separate them. This means the gravitational field binding them together must have negative energy, because you have to put in positive energy to bring the system up to zero. The astonishing claim of the null universe hypothesis is that these two forms of energy, the positive energy of matter and radiation and the negative energy of the gravitational field, cancel each other out with perfect precision. The positive and the negative sum to zero. Think of it like a financial ledger for the entire cosmos. On one side, you have a massive asset column, all the stars, gas, and dark matter. On the other side, you have an equally massive liability column, the gravitational binding energy of everything pulling on everything else. When you add them up, the books balance perfectly at zero. This isn't just a vague philosophical idea. Physicists like Stephen Hawking, Alan Guth, and others have worked through the math, and for a universe that is flat and finite like ours appears to be, the total energy does indeed seem to be zero. This has a profound implication for the origin of everything. In quantum mechanics, the seemingly solid and stable world is governed by probabilities and uncertainties. One of the most bizarre consequences of this is that empty space, or the vacuum, is not truly empty. It is a seething, bubbling foam of virtual particles that constantly pop into and out of existence, borrowing energy from the vacuum for an infinitesimally short time before annihilating and paying the debt back. Because of the Heisenberg uncertainty principle, which allows for these brief violations of energy conservation, something can indeed come from nothing as long as it doesn't last too long. Now, if the total energy of the universe is zero, then our entire cosmos could be one of these quantum fluctuations, albeit on a scale almost impossible to comprehend. It could have tunneled into existence from literally nothing, a stable bubble of space-time that didn't need to borrow any energy because its net energy was and always will be zero. The universe is the ultimate free lunch because it didn't cost anything to make. This concept provides a stunningly elegant and purely physical mechanism for the origin of the universe that requires no external cause or prime mover. It emerges naturally from the combined laws of quantum mechanics and general relativity. It suggests that the question, why is there something rather than nothing, might be based on a false premise. There isn't something and nothing as separate categories. There is only a something whose total energy content is nothing. Our magnificent universe, with its swirling galaxies and conscious beings, could be a vast and complex expression of nothing at all, a fluctuation in the void that achieved permanence through the perfect, beautiful balance of its own internal accounts. Now, let's explore a theory that introduces a deep and elegant symmetry to the very building blocks of reality, a concept that could have been the invisible guiding hand shaping our universe's first moments. This is the theory of supersymmetry, often nicknamed SUSY, and it proposes a fundamental partnership between the two great families of particles, the fermions that make up matter and the bosons that carry forces. It suggests that for every known particle in our cosmic catalogue, there exists a hidden, heavier superpartner, a shadow particle that could solve some of physics' most perplexing puzzles and might even be the key to unlocking the mystery of dark matter. To grasp why this idea is so compelling, we need to understand the hierarchy problem, one of the most frustrating fine-tuning issues in all of physics. It asks why the force of gravity is so unbelievably weaker than the other fundamental forces. The electromagnetic force is 1,000 trillion times stronger than gravity. This is a disparity so vast it seems absurd. In quantum field theory, the mass of a particle like the Higgs boson receives constant corrections from its interactions with virtual particles popping in and out of the vacuum. These quantum fluctuations should drive the Higgs mass, and by extension the mass scale for all particles, up to the highest possible energy, the Planck scale, making them incredibly heavy. Yet somehow the particles we observe are astonishingly light. This suggests an almost miraculous cancellation of these quantum effects, a fine-tuning so precise it feels like a cosmic accident. Supersymmetry offers a breathtakingly elegant solution. It proposes that for every fermion particle of matter, there is a bosonic superpartner, and for every boson force carrier, there is a fermionic superpartner. These superpartners would contribute their own quantum corrections to particle masses, but with the opposite sign. If supersymmetry were perfectly unbroken, these contributions would cancel each other out exactly, solving the hierarchy problem naturally and eliminating the need for any divine or random fine-tuning. The implications of this for the early universe are profound. In the unimaginable heat of the first fractions of a second after the Big Bang, supersymmetry would have been an exact symmetry of nature. Every particle and its superpartner would have had identical masses. This perfect balance would have governed the evolution of the cosmos, influencing how forces unified and how matter coalesced. As the universe expanded and cooled, this perfect symmetry would have been broken, causing the superpartners to acquire their heavy masses, effectively hiding them from our current low-energy view of reality. The energy scale at which this symmetry breaking occurred is thought to be incredibly high, which is why we haven't observed these particles yet with our current particle accelerators. But their influence in those first moments would have been absolutely critical in setting the stage for the universe we inhabit today. One of the most exciting consequences of supersymmetry is its potential to explain the nature of dark matter. The lightest supersymmetric particle, or LSP, is a prime candidate for this mysterious, invisible substance that makes up most of the matter in the cosmos. In most SUSY models, this particle is stable because of a conserved quantum number called R parity, meaning it cannot decay into any ordinary particles. Vast numbers of these particles would have been created in the fiery forge of the Big Bang. As the universe cooled, all the other superpartners would have decayed away, but the lightest supersymmetric particle would have remained, a stable relic from the dawn of time, silently drifting through space and forming the vast gravitational scaffolding upon which galaxies built themselves. Finding this particle wouldn't just confirm a beautiful theory, it would solve one of cosmology's greatest mysteries in a single stroke. For decades, the hunt for these superpartners has been a primary goal of the world's most powerful particle accelerators, like the Large Hadron Collider at CERN. Physicists have been smashing protons together at unprecedented energies, hoping to create these heavy, exotic particles in the lab and observe their decay signatures in the detectors. While the Higgs-boson's discovery in 2012 was a triumphant validation of the Standard Model, it also intensified the search for SUSY, as supersymmetry so elegantly explains how such a light Higgs could exist. So far, the superpartners have remained elusive, pushing the possible mass scale for these particles ever higher and forcing theorists to consider more complex and nuanced versions of the theory. This lack of direct evidence is a significant challenge, but the mathematical beauty and explanatory power of supersymmetry are so great that the search continues with undiminished passion, driven by the hope that we are on the verge of discovering a new, symmetrical layer of reality just beyond our current sight. But what if the universe didn't have a dramatic, explosive birth at all? What if, instead of a singular, cataclysmic event, our cosmos emerged slowly and smoothly from a timeless, eternal state, awakening into expansion like a seed gradually sprouting? This is the captivating premise of the emergent universe scenario, a class of models that offers a serene and elegant alternative to the violent singularity of the Big Bang. The central goal of this scenario is to sidestep one of the most troubling aspects of the Standard Model, the initial singularity. A point of infinite density and temperature is, for physicists, a nightmare, a place where the known laws of physics completely break down and mathematics fails. The emergent universe proposes a much gentler beginning. Imagine a universe that has always existed in a static or nearly static state resembling a cosmic egg. This primordial state isn't empty, it's filled with a special kind of matter or energy field that keeps it in a delicate, meta-stable equilibrium, like a ball perfectly balanced on the tip of a very flat hill. It could have remained in this quiet, unchanging phase for an eternity, with no beginning in time. Then, triggered by a subtle quantum fluctuation or a slow evolution of the field itself, the balance is ever so slightly tipped. The ball begins to roll, and the universe gently transitions from this static state into the period of expansion we observe today, all without ever passing through a state of infinite density. This approach provides a compelling and very different solution to the same cosmic puzzles that inflation was designed to fix. How did the universe become so incredibly large, flat, and uniform? In the emergent universe model, it didn't need a faster-than-light growth spurt to become smooth. It was always smooth, having existed in a stable, unchanging state for an infinite amount of time. The universe had all the time in the world, literally, for any irregularities or wrinkles to naturally iron themselves out through casual contact and thermal equilibrium. The horizon problem simply vanishes because every part of the universe was always in contact with every other part during that eternal static phase. The flatness is also a natural consequence of this long preparatory period, as the geometry of space settles into the most stable, balanced configuration. The mechanism for this requires a specific and somewhat exotic type of substance in the early universe. One of the most common proposals is a cosmic scalar field with a particular type of potential energy, often visualized as a hill with a very flat top. While the universe is sitting on this flat plateau, the field acts like a perfect cosmological constant, providing a repulsive force that exactly counteracts any tendency to contract, maintaining the static state. As this field eventually rolls off the plateau and down the hill of its potential, its energy is converted, reheating the universe and initiating the hot Big Bang expansion we are familiar with. This elegantly provides a bridge from a timeless past to our dynamic present, offering a complete history that never demands a true beginning. The appeal of this model is its philosophical elegance. It presents a universe without a definitive starting gun, a cosmos that simply is, transitioning gracefully from one phase to another. It removes the need for a singularity and the troubling question of what was before. By suggesting there was no before, there was just an everlasting, steady state that eventually evolved. While it shares the eternal nature of models like the steady-state theory, it crucially incorporates the hot, expanding phase and the cosmic microwave background evidence that doomed its predecessor. The emergent universe scenario isn't a challenge to the entire Big Bang framework. Rather, it's an alternative proposal for the very earliest prelude, a different overture to the same magnificent cosmic symphony. It reminds us that the story of our origins might be even stranger and more subtle than a single, brilliant flash of light. While many of our theories rely on the most advanced mathematics of the 21st century, the captivating idea of a cosmic egg reminds us that humanity has been pondering the origin of everything since the dawn of consciousness itself. Across countless cultures and millennia, a strikingly similar image emerges: the universe born from a single, primordial egg cracking open to release all of existence. This is not merely a quaint myth, it is a profound metaphor that resonates deeply with our modern scientific quest, suggesting a universal human intuition about a singular beginning from a state of perfect unity. In the ancient Vedic texts of India, the universe began as a golden embryo, Hiranyagarbha, floating in the void of non-existence. The Rigveda describes this golden womb from which the creator god Brahma was born, who then fashioned the world. Half of the great egg's shell became the sky, the other half the earth, and the yolk became the sun. On the other side of the Himalayas, Chinese mythology speaks of Pan-gu, a giant who slept and grew inside a colossal cosmic egg for 18,000 years. When he awoke and broke free, the lighter, pure parts of the egg floated up to form the heavens, while the heavier, turbid parts sank down to create the earth. His body itself then became the mountains, rivers, and stars, a universe born from a single being. This theme echoes in the myths of the Orphic tradition in ancient Greece, where the protogenous Phanes, the deity of procreation, hatched from a cosmic egg fashioned by Kronos, time itself, in the boundless womb of ether. These stories are far more than coincidental folklore. They represent a shared human attempt to conceptualize the inconceivable. Before telescopes and particle accelerators, the cosmic egg served as the perfect symbol, a self-contained, finite object holding infinite potential. It represents a state of perfect symmetry and unity, where all the elements of the cosmos are compressed together, undifferentiated and whole. The act of cracking or breaking is the moment of symmetry breaking, the instant where the single unified force of creation fractures into the myriad diversity we see around us: light and dark, earth and sky, matter and energy. It is a poetic and powerful analog for the Big Bang singularity, a point of infinite potential whose cracking open was the violent onset of inflation and expansion. Modern cosmology has, in a way, brought us full circle back to this ancient symbolism, the concept of the universe starting as a Planck-sized speck of unimaginable density is our scientific cosmic egg. When scientists describe the rapid expansion of space-time, they might as well be describing the shell of that egg expanding outward, creating the separation between galaxies and the vast cosmic voids. Even the cosmic microwave background radiation, the oldest light we can see, can be imagined as the lingering warmth from that initial universe-spanning incubation. Artists have long been drawn to this powerful imagery, creating stunning representations of a luminous egg cracking against the blackness of space, with nebulae and galaxies streaming from its fissures, visually bridging the gap between ancient wonder and contemporary understanding. This enduring symbol connects our most primal stories to our most advanced theories, reminding us that the desire to understand our origins is a fundamental part of what makes us human. This profound connection between time and disorder leads us to one of the most compelling pieces of evidence for a cosmic beginning, one written not in ancient light but in the inevitable crumbling of all things. This is the thermodynamic argument, a powerful line of reasoning that uses the universally observed increase of entropy to peer back into time and deduce that our universe must have started in a state of exceptionally low entropy, a condition of exquisitely fine-tuned order that begs for an explanation. The second law of thermodynamics is arguably the most non-negotiable rule in all of physics. It states that the total entropy, a measure of disorder or randomness of an isolated system, always increases over time. It's the reason your coffee cools down instead of spontaneously heating up, why a dropped egg splatters into a mess but a mess never reassembles itself into a whole egg, and why we remember the past but not the future. This law gives us a powerful arrow of time, pointing inexorably from a more ordered past toward a more disordered future. Now, if we follow that arrow backward, we are forced to a startling conclusion. The fact that entropy is still increasing today, some 13.8 billion years after the Big Bang, means that the universe must have begun in a state of incredibly low entropy. It was, in a sense, wound up like a perfect cosmic spring at the moment of its creation, and everything that has happened since has been the slow, irreversible unwinding of that spring. Our observable universe today is a fascinating mix of order and disorder. We see breathtaking structures like spiral galaxies, solar systems, and living organisms, which are pockets of incredibly low local entropy. But these are all temporary, maintained by constantly consuming energy and exporting disorder elsewhere. The sun, for instance, creates the delicate order necessary for life on Earth by generating a far greater amount of disordered radiation that it blasts out into the cold of space. The overall trend is unmistakable. The universe is relentlessly evolving from its initial state of low entropy toward a final state of maximum entropy, a featureless, lukewarm soup where no energy can be harnessed and no meaningful events can occur, the heat death we call the cosmic grave. So what did this incredibly special low entropy initial state look like? For a long time, physicists thought it might be something like a perfectly uniform gas of particles, neat and symmetrical. But a uniform gas is actually a state of high entropy. The real low entropy state of the early universe was something far more specific and surprising. It was the energy of the universe being locked up not in matter, but in the gravitational field itself. The tremendous gravitational clumping we see today, the stars, galaxies, and black holes, represent a state of high gravitational entropy. The low entropy beginning was a state where matter and energy were spread out with near-perfect smoothness. The universe started smooth and has been clumping up gravitationally ever since, which is the primary driver of the increase in entropy we observe. The cosmic microwave background is our direct snapshot of this initial smoothness, a picture of the universe when it was a bland, hot plasma with only tiny, faint ripples that would one day become the seeds of all structure. This presents one of the deepest mysteries in all of science, known as the past hypothesis. Why was the entropy of the universe so unimaginably low in the past? The laws of physics themselves don't demand it. They work perfectly well running forward or backward. A universe that started in a state of high entropy would already be in thermal equilibrium, and nothing interesting would ever happen. No stars, no planets, no physicists to ask why. The fact that it didn't, that it started in this incredibly improbable, finely tuned configuration, is the foundation upon which all of history, and indeed our own existence, is built. Some theorists, like Sean Carroll, argue this points to a need for a deeper explanation, perhaps involving the multiverse. In an eternally inflating multiverse, while most regions are high entropy dead zones, rare quantum fluctuations can pop into a low entropy state, and we naturally find ourselves in one of those rare, life-permitting bubbles. Others see it as the ultimate clue, the fingerprint of a fundamental law of initial conditions that we have yet to discover, a rule that dictated the universe must start this way. Whatever the answer, the undeniable thermodynamic arrow of time points firmly to a beginning that was not just a moment of extreme energy, but a moment of exquisite and inexplicable order. Now, if the ultimate free lunch of a null universe seems almost too elegant to be true, it forces us to confront the fundamental schism at the heart of modern physics, a divide so deep that it prevents us from fully understanding that very first moment. For decades, our two most powerful descriptions of reality have been locked in a stalemate. On one hand, we have Einstein's general relativity, which masterfully paints the cosmos on its largest canvas, describing the graceful curvature of space-time by massive objects like stars and black holes. On the other, we have quantum mechanics, which with astonishing precision governs the bizarre, probabilistic world of the atom. The problem is, these two titans of physics speak completely different languages and obey different rules. Uniting them into a single, coherent theory of quantum gravity is perhaps the greatest challenge in all of science, and it's a challenge we must overcome to ever truly know what happened at the singularity. The conflict is stark. General relativity is a classical theory, smooth and deterministic. It tells us that space-time is a continuous fabric, warping in a predictable way. Quantum mechanics, however, is built on uncertainty, quantization, and probability. When we try to apply quantum rules to the gravitational field, the mathematics explodes into nonsense, producing infinite probabilities that make no physical sense. This breakdown isn't just a mathematical inconvenience, it's a sign that our theories are incomplete. To describe the universe's birth, where everything was compressed into a space smaller than an atom, we desperately need a framework where gravity is quantum. Without it, the Big Bang singularity remains a permanent veil over our eyes, a place where our science simply stops. One of the most promising, yet less mainstream, approaches to this problem is known as asymptotic safety. The name sounds complex, but the core idea is beautifully intuitive. In quantum field theory, the strength of a force, its so-called coupling, constant changes with the energy at which you measure it. This is called running. For some forces, like the strong nuclear force, this running makes the force weaker at higher energies, a property known as asymptotic freedom, which won its discoverers a Nobel Prize. Asymptotic safety proposes that gravity might possess a similar but slightly different property. Instead of becoming weak, the strength of gravity could be guided by an ultraviolet fixed point, a kind of cosmic attractor in the mathematical landscape. As we zoom into the incredibly high energies of the Big Bang, the frantic quantum fluctuations that normally cause those destructive infinities would be precisely counterbalanced by this fixed point, taming the math and allowing gravity to be consistently described at all scales. Imagine an adventurous kayaker heading downstream toward a treacherous waterfall. The waterfall represents the singularity where our physics breaks down. Normally, the current would pull them inexorably over the edge. But if the river had a perfect, stable whirlpool just before the drop, the kayaker could paddle into it and circle safely forever, never needing to go over the fall. In this analogy, the ultraviolet fixed point is that stable whirlpool. It would allow the equations of quantum gravity to be well-defined and finite all the way to the highest energies, providing a complete, self-consistent description of the universe's birth without any singularities. The theory suggests that at the Planck scale, space-time itself might be composed of a fractal-like structure, a swirling, space-time foam where tiny wormholes constantly blink in and out of existence, a concept first proposed by John Wheeler. The implications for cosmology are profound. An asymptotically safe theory of gravity could naturally avoid the initial singularity, replacing the Big Bang with a smooth quantum bounce from a previous cosmic phase or a transition from a timeless state. It could provide a physical mechanism for the incredibly low entropy initial condition, perhaps showing that the smooth, flat universe was the only possible outcome from the quantum gravitational vacuum. Researchers have used this approach to explore the universe's very first moments, finding that the violent quantum fluctuations could have automatically generated a period of inflation, eliminating the need for a separate inflaton field. It's a powerful, minimalist proposal that uses the inherent quantum nature of gravity itself to solve the puzzles of our origin. However, the path to proving asymptotic safety is fraught with immense challenges. The mathematics involved is formidably complex, requiring sophisticated approximations to navigate the infinite possibilities of spacetime geometry. Unlike string theory or loop quantum gravity, it doesn't necessarily predict dramatic new phenomena like extra dimensions or discrete spacetime at accessible energies. Its smoking gun would be a very precise measurement of how gravity behaves at distances we cannot yet probe. Despite these hurdles, the pursuit of a theory of quantum gravity, whether through asymptotic safety, strings, loops, or another path, remains the holy grail of fundamental physics. It's the essential key that will finally unlock the door to our cosmic dawn, allowing us to move beyond informed speculation and into a true understanding of how everything, from the laws of physics to the fabric of spacetime, first came to be. But as we consider the universe's smooth beginnings, a radical theory suggests that its grandest structures might have been seeded by the darkest objects imaginable. This is the fascinating idea of primordial black hole seeding, a concept proposing that vast numbers of tiny, ancient black holes forged in the chaos of the Big Bang could be the hidden architects of our cosmos and perhaps even the mysterious substance we call dark matter. Unlike the stellar black holes we know today, which form from the collapse of massive stars, primordial black holes are thought to be a product of the universe's incredibly dense and turbulent infancy. In the first second after the bang, extreme density fluctuations could have caused pockets of space to collapse directly under their own gravity, bypassing the need for a star entirely. These hypothetical objects could range in size from smaller than an atom to larger than a star, with a mass anywhere from a small asteroid to hundreds of thousands of suns, making them a uniquely versatile candidate for shaping the universe. The theory offers an elegant solution to one of astronomy's greatest challenges. How did galaxies form so quickly? Observations from the James Webb Space Telescope are revealing fully formed galaxies at astonishingly early cosmic times, a development that challenges our standard models of gradual gravitational growth. If the early universe was already peppered with heavy primordial black holes, they would have provided ready-made gravitational anchors around which the first stars and gas could rapidly accumulate. These black hole seeds would act as cosmic catalysts, jump-starting the formation of galactic cores and helping to build the immense structures we see in the distant universe far faster than gravity alone could manage. This could explain the surprising maturity of early galaxies and provide a missing link in our story of cosmic evolution. Perhaps even more compelling is the possibility that these ancient relics could solve the 85-year-old mystery of dark matter. All the stars, planets, and visible gas in the universe account for less than 20% of the total matter we know must exist from its gravitational pull. The rest is dark matter, an invisible substance that holds galaxies together and shapes the cosmos on the largest scales. While the leading candidate has been a hypothetical weakly interacting massive particle, or WIMP, decades of searches have come up empty. Primordial black holes present a compelling alternative. They are, by their very nature, dark, and they certainly have mass. If vast numbers of them were created in the early universe and still drift through space today, they could collectively account for the gravitational effects we attribute to dark matter, all without requiring any new fundamental particles beyond those already in the standard model. The hunt for these elusive objects is a testament to scientific creativity, as researchers employ an astonishing array of detection methods. One of the most promising techniques is gravitational microlensing. If a primordial black hole passes directly between Earth and a distant star, its gravity will act like a lens, bending the starlight and causing the star to temporarily brighten in a characteristic way. Surveys like the optical gravitational lensing experiment and Subaru's hyper-subprime cam are constantly monitoring hundreds of millions of stars, searching for these telltale flashes that betray the presence of an invisible, massive object. Other methods include looking for the distinctive ripples in space-time gravitational waves, emitted when two primordial black holes spiral into each other and merge, events that have been detected by observatories like LIGO and Virgo. Some theories even suggest that these ancient black holes could influence the cosmic microwave background or disrupt the delicate structures of star clusters, leaving subtle imprints for astronomers to decipher. The cosmological impact of this theory is profound, weaving these dark objects into the very fabric of our existence. If primordial black holes are indeed common, they would not just be passive inhabitants of the cosmos but active participants in its evolution. They could trigger the formation of the first stars, dictate the assembly of galaxies, and ultimately determine the large-scale architecture of the universe. Their distribution could explain why galaxies are clustered the way they are, and why some dwarf galaxies seem to be overwhelmingly dominated by dark matter. The quest to find them pushes our observational capabilities to the limit, blending the science of the very large with the physics of the very small, and reminding us that the answers to the universe's biggest questions might be hiding in the darkest corners of space, waiting for the light of our curiosity to find them. But while inflation has become the leading explanation for our universe's smoothness, it's not the only game in town. Another truly radical idea suggests that the cosmic speed limit itself might not be as constant as we believe. This is the variable speed of light theory, or VSL, a provocative proposal that in the universe's first fleeting instance, light traveled at a rate far exceeding its modern speed, offering a dramatic alternative to the inflationary paradigm for solving those same deep cosmic puzzles. The constancy of the speed of light is a cornerstone of modern physics, enshrined in Einstein's theory of relativity. In a vacuum, light always travels at 299,792,458 meters per second, and this universal speed limit is woven into the very fabric of spacetime, connecting energy to mass and governing causality. But what if this fundamental constant wasn't always so constant? Proponents of VSL, like renowned physicist Joe Megiddo, argue that in the extreme environment of the primordial universe, the laws of physics as we know them may not have fully crystallized. They propose that the speed of light could have been orders of magnitude greater, an idea that initially seems to shatter a foundational pillar of science but could instead provide a more elegant solution to the problems inflation was created to solve. The central appeal of this theory lies in its stunning simplicity. The horizon problem exists because in the Standard Model, distant regions of the universe never had time to communicate and equalize their temperature before being carried out of causal contact by expansion. Inflation solves this by expanding space itself faster than light could travel. The variable speed of light theory tackles the problem from the opposite direction. Instead of making space expand faster, it suggests that light itself moved faster, allowing a thermalizing signal to race across the entire infant cosmos in time to smooth it out before the expansion could isolate different regions. It's a beautifully straightforward concept. If you can't bring the regions closer together quickly enough, just allow the information connecting them to move much, much faster. This approach also handily addresses the flatness problem. The incredible geometric flatness we observe indicates a perfect balance between the expansion rate and the gravitational pull of all the matter and energy in the universe. Maintaining this balance over billions of years requires an initial fine-tuning of almost impossible precision. A faster speed of light in the early universe would have fundamentally altered the strength of gravity and other forces, naturally driving the cosmos toward this flat state without requiring any miraculous initial conditions. The universe wouldn't need to be born perfectly balanced. The physics of those first moments would have pushed it relentlessly toward that inevitable equilibrium. The implications of this idea are profound, reaching far beyond cosmology into the heart of fundamental physics. If the speed of light is variable, it forces us to re-examine other constants of nature. Perhaps the fine structure constant, which governs the strength of electromagnetic interactions, also fluctuated. Maybe the fundamental forces themselves unified and separated at different energy scales than we currently predict. This theory doesn't just change a single number, it potentially rewrites the entire thermal history of the universe, suggesting that the constants we hold sacred are not immutable but were forged in the fire of the Big Bang, settling into their current values as the cosmos cooled and found its stable form. Naturally, such a bold challenge to Einstein's relativity faces significant hurdles. The entire edifice of modern physics is built on the constancy of light speed, and altering it requires a meticulous restructuring of our theories to avoid logical inconsistencies and paradoxes, particularly around causality. Proponents have developed sophisticated mathematical frameworks where the variation occurs in a way that preserves a deeper underlying principle, but the work is complex and ongoing. Furthermore, finding definitive evidence is a monumental task. Some have looked for subtle imprints that a changing speed of light might have left on the cosmic microwave background or in the observed abundances of light elements from Big Bang nucleosynthesis. While no smoking gun has been found, the search continues, driven by the powerful allure of a theory that could simplify our cosmic origin story by changing one of our most fundamental assumptions about the nature of reality itself. Imagine our universe not as a solitary island of reality, but as a single page floating in a vast, higher-dimensional library, surrounded by a swirling, dynamic fog of other pages, strings, and membranes. This is the captivating vision of brain gas cosmology, a theory that emerges from the deepest mathematical layers of string theory to offer a radical new story for our cosmic origins, one where the very number of dimensions we experience is the result of a primordial battle for survival. In this framework, the entirety of what we know, all of space, time, matter, and force is confined to a three-dimensional membrane, or simply a brain. Our home brain is not alone. It exists within a sprawling, higher-dimensional reality known as the bulk, which is filled with a chaotic, simmering soup of other objects. There are one-dimensional strings, two-dimensional membranes, and other three brains like our own, all whizzing about and interacting in a dizzying cosmic dance. The very early universe, in this view, was not a point of infinite density, but a hot, dense gas of these fundamental ingredients, all existing in a space with 9 or 10 spatial dimensions. The initial conditions weren't a perfectly tuned set of constants, but a random, energetic mess of vibrating brains. The central, brilliant insight of this model is how it explains why we live in a universe with exactly 3 spatial dimensions that are large and observable. In the scorching heat of the beginning, all dimensions were compact, curled up, and tightly wound. As this brain gas began to cool, a fascinating evolutionary struggle began. According to the mathematics of string theory, brains of different dimensions interact and evolve according to their own specific laws. Crucially, the expansion of dimensions isn't automatic. It's a physical process where some dimensions manage to grow while others remained imprisoned at the tiniest possible scale. The reason we have 3 large spatial dimensions, the theory suggests, is that only brains of a certain dimensionality can efficiently avoid annihilating each other. One-dimensional strings and 2 brains are much more likely to find each other in this higher dimensional space and collide, mutually annihilating in a burst of energy. But 3 brains are far more stable. Their interactions are less frequent, their paths less likely to cross in a way that leads to destruction. Over unimaginable eons, the unstable brains and strings cancelled each other out while the robust 3 brains survived and thrived. As they did, the dimensions to which they are attached were able to stretch and expand. The 3 dimensions we call length, width, and height are large and expanding not because of a special initial property, but because the three brains that govern them won the cosmic lottery of stability. The other 6 spatial dimensions remain curled up and tiny at every point in space because the objects that could have catalyzed their expansion, the 1 and 2 brains, largely destroyed themselves in the early melee. This provides a breathtakingly elegant and naturalistic explanation for one of the most basic yet profound facts of our existence: why our universe has the structure it does. There's no need for a creator to carefully select 3 dimensions. It was the inevitable outcome of a brutal process of cosmological natural selection playing out in the higher dimensional bulk. The initial hot, dense state naturally evolves into the cosmos we see, with the number of dimensions set by the last brain standing. This model also offers a compelling alternative to the inflationary paradigm for explaining uniformity. The random thermal motions and interactions within the brain gas could have naturally smoothed out the universe over time, as the chaotic jostling of countless objects led to a state of equilibrium, eliminating the need for a separate, hyper-fast expansion period to achieve the incredible smoothness we observe in the cosmic microwave background. It's a story where our comfortable, 3-dimensional reality is the lasting echo of a violent, multi-dimensional battle that was fought and won in the first moments of time. Yet for all the grandeur of these higher dimensional battles, they lead us to a profoundly different vision of cyclical rebirth, one that replaces the fiery collision of brains with the gentle, inevitable rhythm of cosmic breathing. This is the heart of the bouncing cosmology, a compelling class of theories that imagines our universe not as a one-time creation event, but as the latest chapter in an endless saga of collapse and renewal. Instead of a definitive beginning at a singular point of infinite density, this model proposes that our cosmos undergoes a perpetual cycle of expansions and contractions, with each Big Bang merely the turning point, the moment of a great bounce, where a collapsing universe reverses its course and blossoms into a new expansion. The driving motivation behind this idea is to eliminate the troubling singularity that plagues the standard Big Bang model. A point of infinite density is where our known laws of physics break down completely. It's a dead end for scientific inquiry. The bounce offers a graceful alternative. Picture a universe collapsing under its own immense gravity, heading toward what would classically be a big crunch. In the final moments of this collapse, as matter and energy are squeezed to unimaginable densities, the bizarre rules of quantum mechanics would take center stage. According to quantum theory, there is a fundamental limit to how precisely we can know both the position and momentum of a particle. This Heisenberg uncertainty principle implies that you cannot crush the universe into a true mathematical point of zero volume. There is a smallest possible size. As the collapsing universe approaches this quantum limit, a powerful repulsive force generated by the quantum properties of matter and space-time itself would overcome the pull of gravity. This wouldn't be a collision with another universe, but an internal rebound, like a cosmic rubber band snapping back after being stretched to its limit. The immense energy of the collapse would be converted into the heat and motion of a new expansion, birthing a new cosmic cycle without ever passing through a state where physics fails. This concept of a quantum bounce is given concrete mathematical form in theories like loop quantum gravity. Here, the fabric of spacetime is not smooth and continuous but woven from discrete, finite loops. This granular structure provides a natural barrier to infinite compression. As the universe collapses, the density eventually becomes so great that it can no longer increase. This maximum density triggers a smooth transition from contraction to expansion, a cosmic bounce that transforms the end of one universe into the beginning of the next. The model provides a complete, singularity-free history, offering a powerful vision of an eternal, self-sustaining cosmos where each cycle inherits a refined state from the one before it. The incredible smoothness and flatness we observe today could be a natural consequence of the immense forces involved in each bounce, which would have stretched and ironed out the wrinkles from the prior universe's chaotic death throes. The implications of a bouncing cosmology are nothing short of revolutionary for our understanding of time and existence. It presents a universe without a true beginning or end, an eternal entity constantly recycling itself. This neatly sidesteps the perplexing metaphysical question of what caused the Big Bang or what existed before it. In this view, there was no before, only a previous cycle in an infinite sequence. Each cycle would effectively reset the cosmic clock, though some models suggest that subtle information or imprints might be carried over from one incarnation to the next. This could potentially explain the initial conditions of our universe without appealing to miraculous fine-tuning or inflation. The low entropy starting point that so puzzles cosmologists might be a natural outcome of the thermodynamic processes occurring during the bounce phase of the previous cycle. It paints a picture of a cosmos that is immortal and resilient, forever dying and being reborn in a majestic, impersonal dance that makes our entire history just one verse in an infinite cosmic poem. What if the most fundamental ingredient of reality isn't matter or energy, but something far more ethereal and powerful, information itself? This brings us to a theory that reframes the entire cosmic narrative, suggesting the universe didn't emerge from a physical singularity, but from a primordial state of pure data processing. In the information theoretic view, reality is not made of particles and forces in the traditional sense, but of bits and computations. The cosmos is not a great mechanical clockwork, but a vast cosmic computer, and the laws of physics are simply the algorithms it is running. This radical perspective finds its roots in the work of pioneering thinkers like John Archibald Wheeler, who famously proposed it from bit. Wheeler suggested that every particle, every force field, and even the fabric of space-time itself ultimately derives its existence from binary answers to yes or no questions. In this view, the universe is participatory. We are not just passive observers, but part of an informational loop where the act of observation helps to define reality. This idea was pushed even further by Konrad Zuse, a German engineer who, in the 1960s, was one of the first to seriously propose that the universe could be a giant digital computer, a cellular automaton calculating its own state from one moment to the next. The evidence for this isn't found in telescopes, but in the deep structure of physics itself. Consider a black hole. Jacob Bekenstein and Stephen Hawking discovered that the maximum amount of information you can store in any region of space is not proportional to its volume, but to the surface area of its boundary. This is a huge clue. It suggests that the three-dimensional world we experience might be a projection of information encoded on a two-dimensional surface, much like a hologram. The information describing everything within a volume is somehow smeared across its outer edge. This holographic principle strongly implies that information is more fundamental than space, time, or matter. The universe might be fundamentally two-dimensional, and our perception of three spatial dimensions is a kind of incredibly convincing illusion. This leads us directly to the heart of digital physics and the concept of the universe as a computation. If reality is informational, then what we perceive as the unbreakable laws of physics might be the operating code of the cosmos. The relentless forward march of time could simply be the sequential processing of this cosmic program, one Planck time step after another. The apparent randomness of quantum mechanics might be the output of a deterministic random number generator buried deep in the source code. In this view, the Big Bang wasn't a physical explosion, but the moment the cosmic computer booted up, initializing the variables of space-time and energy, and beginning the great calculation that has unfolded for 13.8 billion years. The implications of this are as profound as they are bizarre. It suggests that searching for a traditional theory of everything might be missing the point. Instead of a single, elegant equation that describes a force field, the ultimate law might be an algorithm, a set of rules for a cosmic cellular automaton. Our quest would then shift from discovering what the universe is to reverse engineering the program it is running. This also offers a potential, albeit speculative, answer to the question of why the universe is comprehensible at all to the human mind. If the cosmos is computational, then it is inherently mathematical and logical, and our own minds, products of that same universe, are naturally equipped to understand its rules. We are, in a sense, the universe's way of understanding its own source code. This perspective doesn't diminish reality. It transforms it into the most epic story ever written, a narrative not of atoms and energy, but of information becoming aware of itself. Yet if the universe truly is an information processor, it begs the ultimate question: could it have written its own source code? This leads us to a theory of breathtaking self-sufficiency, the idea of a self-creating universe, a cosmos that requires no external architect, no prior dimensions, and no supernatural cause because it contains the reason for its own existence within the elegant, self-consistent, and self-referential nature of its own physical laws. In this view, the universe isn't just here, it logically must be here, a necessary consequence of a mathematical and physical structure that is its own first cause. This concept, sometimes called the self-explaining universe, pushes against one of our most fundamental intuitions, that every effect must have a preceding cause. We look for the cause of the Big Bang, but this theory suggests that at the level of the entire cosmos, this chain of causality might loop back on itself in a perfectly consistent closed loop. Imagine a snake eating its own tail, but instead of a paradox, it forms a stable, logically consistent circle. The laws of physics aren't just descriptions of how the universe behaves, they are the very reason it can exist at all. They act as both the blueprint and the builder, the question and the answer, bootstrapping reality into existence from a state of pure potentiality defined by mathematical consistency alone. One of the most compelling frameworks for this is the concept of the universe as a self-consistent solution to its own equations. In the same way that the number zero exists as a necessary concept within mathematics, the universe might exist as a necessary consequence of a particular set of self-consistent physical laws. The physicist John Wheeler captured this with his idea of law without law, suggesting that the laws of physics themselves might have emerged from a primordial chaos through a process of self-organization, eventually settling into the stable, ordered patterns we observe today. The universe isn't obeying rules imposed from the outside. It is the physical manifestation of a deeply mathematical truth that simply had to be. Its existence is its own explanation. The philosophical implications of this are staggering, directly confronting centuries of debate about a first cause or an unmoved mover. It offers a purely naturalistic resolution to the problem of creation, removing the need for any entity outside of nature to kickstart the process. The universe doesn't need a creator because it is, in its entirety, a self-contained causal loop. This doesn't make it any less marvelous. In fact, it makes it more profoundly beautiful. Its existence is not a contingent accident but a logical inevitability. We find ourselves in a cosmos that is not just lawful, but necessarily so, a reality that could not have failed to exist in some form, because its potential for being is woven into the very fabric of logic and mathematics. It's a vision that replaces a divine creator with a different kind of miracle, the awe-inspiring power of self-consistency, where the universe is both the greatest mystery and its own perfect solution. And so we arrive at the final frontier of our cosmic journey, the ultimate dream that has guided physics for over a century, the quest for a single, elegant framework that can perfectly describe the universe's very first moments. This is the search for a theory of everything, a final unification that would weave together all the forces of nature and all the particles of matter into one magnificent, seamless tapestry of physical law. It is the hope for an equation so profound that it could be written on a T-shirt, yet powerful enough to encapsulate the entire history of the cosmos, from the quantum foam of the first instant to the grand spiral galaxies we see today. This dream is not new. One can almost picture Albert Einstein in the later years of his life, alone in his study at Princeton, surrounded by blackboards covered in intricate tensors and symbols, desperately seeking a unified field theory. He yearned to show that gravity and electromagnetism were not two separate forces, but different manifestations of a single, underlying principle governing the geometry of spacetime. Though he never found it, his unwavering belief that the universe is ultimately simple and comprehensible at its deepest level lit a fire that continues to burn in the hearts of theoretical physicists. His quest was for a theory so complete that it would leave no room for arbitrary constants or unexplained coincidences. A theory where everything that happens because it cannot happen any other way. Today, that torch is carried by two magnificent yet fiercely competitive frameworks, string theory and loop quantum gravity. String theory, as we've explored, offers a vision where the endless diversity of particles and forces are simply different vibrational notes played on tiny, fundamental strings. Its allure is its breathtaking power to unify gravity with quantum mechanics within a single mathematical structure, but the cost is a universe with 10 dimensions and a nearly infinite landscape of possible realities. Loop quantum gravity, on the other hand, takes a more minimalist approach. It doesn't seek to unify all forces at once, but instead focuses on applying the rules of quantum mechanics directly to the fabric of spacetime itself, quantizing it into a web of finite, interwoven loops. It offers a compelling vision of a universe that avoids a true singularity through a cosmic bounce, but it has yet to successfully incorporate the other fundamental forces into its core. The frustrating and yet utterly captivating reality is that both of these theories are currently like magnificent castles in the air, beautiful, internally consistent, and intellectually dazzling, but built without a single experimental pillar to confirm they are actually descriptions of our reality. They make predictions, but those predictions concern energies a quadrillion times higher than what our most powerful particle colliders can reach, or phenomena occurring at scales a billion times smaller than an atom. We are like architects who have deduced the possible blueprints for a cathedral by studying a single grain of sand found on its doorstep. The mathematics is compelling, but the connection to our physical world remains profoundly indirect. This is why the true final theory will not be complete until it makes a prediction we can actually test. The dream is to find a smoking gun signature from the early universe that only one theory can explain. Perhaps it will be a specific, faint pattern twisted into the polarization of the cosmic microwave background, the imprint of primordial gravitational waves from inflation, which could tell us about the energy scales at play. Maybe it will be a subtle deviation in the behavior of particles at extreme energies, a tiny crack in the standard model that points towards supersymmetry or extra dimensions. Or it could be something entirely unexpected, a cosmic surprise that forces us to rewrite the rules once again. The final theory won't just be a mathematical curiosity. It will be a tool that allows us to rewind the cosmic film with confidence, to watch the moment time itself crystallized from a timeless quantum potentiality, and to finally understand why there is a universe at all. Ultimately, the quest for this final unification is about more than just physics. It is a fundamental human yearning to understand our place in the cosmos. It is the modern embodiment of humanity's oldest and most persistent question. Why are we here? To find that equation would be to touch the mind of the universe, to see the underlying logic and beauty that has given rise to black holes, stars, planets, and life. It would be the greatest intellectual achievement in human history, a testament to the power of curiosity and reason. And while we may not be there yet, the very act of searching, of pushing the boundaries of thought and imagination, is a glorious celebration of what it means to be a conscious part of this astonishing, self-aware universe. From the violent inception of the Big Bang to the serene emergence from a timeless state, From cyclical collisions in higher dimensions to a universe born from a quantum fluctuation in nothingness, our journey through these 30 theories reveals a breathtaking tapestry of human curiosity and ingenuity. We've ventured into the strange realms of holographic projections and cosmic simulations, explored the possibility that our entire existence is just one bubble in an infinite multiverse, and even considered that the very fabric of reality might be woven from pure information. Each theory, in its own unique way, is a testament to our relentless drive to answer the most profound question of all: where did everything come from? What's truly remarkable is that this isn't just a collection of wild guesses. Every one of these ideas is grounded in rigorous mathematics and a deep understanding of physics, even when they take us to the very edge of what is testable and knowable. They represent the leading edge of cosmology, where the brightest minds on the planet are grappling with concepts that defy our everyday intuition. The fact that such a diverse range of compelling models can exist simultaneously doesn't show a failure of science, but rather its greatest strength: an open-minded, creative, and constant pursuit of truth, even when that truth is more bizarre than any work of fiction. Yet for all our progress, the ultimate origin of the universe remains one of the greatest unsolved mysteries. We are like detectives who have arrived at the scene 13.8 billion years after the fact, piecing together clues from the faint afterglow of creation and the large-scale structure of the cosmos. Each new discovery, from the detailed maps of the cosmic microwave background to the detection of gravitational waves, helps us rule out some possibilities and refine others. But the final answer continues to shimmer just beyond our grasp, reminding us that the universe is under no obligation to make sense to us, and that wonder is an essential part of the human experience. This ongoing quest is about more than just satisfying our curiosity. It's a fundamental part of understanding our own place in the cosmos. By learning how the universe began, we learn what it is made of and how it works. This knowledge, in turn, tells us about the long-term fate of all things and the conditions that made our own existence possible. We are stardust engaged in a cosmic dance that began in the first fleeting moments of time, and now we are trying to understand the music. The search for our origins is, in the end, a search for ourselves. The conversation doesn't end here. This is one of the most dynamic and exciting fields in all of science, with new ideas and discoveries emerging all the time. Now we want to hear from you. Which of these theories resonates the most with your own sense of wonder? Do you find the quantum fluctuation idea elegant, or does the cyclic model feel more complete? Perhaps you have your own favorite that we didn't get to cover. Share your thoughts and questions in the comments below. We absolutely love diving into these discussions with you. If you enjoyed this journey to the beginning of everything, make sure to subscribe and hit the notification bell so you don't miss our next exploration into the mysteries of the cosmos. From the enigmatic nature of black holes to the search for alien life, there's a whole universe of topics waiting for us to explore together. Thank you for joining us on this incredible adventure, and never stop asking the big questions. After all, it's that sense of wonder that truly makes us human.